Okay, so we're officially recording. All right, so I wanted to just review. I know it's been a while, so you've traveled, came back, or I guess maybe you're still away from campus, but it's been a while since you have thought about UV radiation in different regions. So I just wanted to show this briefly, just to remind you again that UVC is the most energetic radiation, so it's got the shortest wavelength, okay, and it will have the highest frequency, in other words. And then UVA and B are the ones that we want to, use sunscreen to protect us against. Okay, so UVC is so energetic, it's actually absorbed by oxygen in the atmosphere, and we're going to talk about those reactions here today, really. Okay, so, whoops. So, UV radiation then has sufficient energy to cause certain bonds to break. And so remember the difference between oxygen and ozone. If we look at their Lewis structures, so that's oxygen. And then ozone, remember, was this. I'm going to draw it like this, where it's a bent molecule. We haven't taught shapes yet. That'll be the next chapter. But just to kind of throw this out there now. That, and then this. Okay, so hopefully this looks familiar to you. So this we called resonance structures or resonance forms. Because it really exists as so ozone exists as either of those, kind of a mixture of those two. And so if you're looking here that UV light below 242 nanometers, so if it's less than that, that's UVC. It'll break apart oxygen, so that's strong enough to break apart the double bonds. Okay, but you don't need as much energetic radiation to break apart these ones. Okay, so it exists as kind of like between a single and a double bond. Okay, and so I want to kind of show you. I put it in the slides so that when you watch this online, I'm going to put these, by the way, the recordings of all these, I'm going to put on Blackboard, afterwards. So like later this afternoon, it'll be available for you. And so if you click on this link, you'll go to a variety of simulations. Which one is it? Got a lot of things open. Here we go. So you'll see a variety of simulations that are kind of cool that will be useful maybe for your future classrooms or for you right now this semester to kind of play around with. This one, so the first one I want to show you is the electromagnetic spectrum. And this is kind of cool that you can get the inverse relationship between frequency and wavelength. And so you just drag this bottom green triangle and you can see, as you're dragging it toward the blue, then frequency is going up. Okay, energy is also going up. Okay, and it's in units of electron volts, but you can see, the energy is going up, and then as you drag it all the way from blue to red, then frequency and energy are going down. Okay, so and then up here you can see what happens to wavelength. So wavelength is getting bigger. Okay, as you go to the red, I guess that is. Yeah. Okay, so so that's kind of the first one. And then we're going to talk about some of these others later today. But there's all kinds. There's, this one about UV in the atmosphere kind of walks you through the different regions and, where oxygen versus ozone are located. And then there's some on sunscreens that we're going to talk about later today. And then quite a few on climate change that is for the next chapter. So kind of a good website to kind of bookmark for future. All right. All right, and as always, I know we're not face to face, but if you have any questions, want me to stop, or go back a slide or whatever, just feel free. Just make sure your mics are unmuted, and just tell me, and I'll explain more or go back or whatever. Okay. Now, talking skin damage by UV. Again, UVA and UVB are dangerous. UVA actually goes further into skin. I'm going to show that in the next slide. But here's some trends. It's actually interesting. We've got white males with the highest incidences of skin cancer. So this is rates per 100,000 people. And then next are white females, and then we've got African American males, females down here. So what do you think are some reasons why white males in particular are much higher, like double, triple almost of what females are? Why this difference here? Any ideas? No comments? Okay, I guess not. So probably it's a couple reasons. Probably like white males on average work outside more frequently than white females or than other groups, and we're notorious for not wearing sunscreens too. So it's kind of a manly thing not to put on sunscreen, and so I often go out without it myself too. I know I should have it on, but you're rushing to do something and whatever. Okay, so the higher incidence of skin cancer, whites in general, Caucasian versus African American with more natural melanin, okay, in their skin. So this is what I was talking about. I think I showed this too before, but UVA, even though it is less energetic, it actually goes farther into the skin, and so that causes more skin cancer actually, just because it is not absorbed. It's not so reactive. Like UVB is so reactive, it'll react with epidermal cells, whereas UVA is a little less, so then it will go down to these regions, which studies show this is it causes a lot more skin cancers, so carcinomas. Okay, and so it's just, I guess, reviewing UVC, UVB, and UVA differences between those. Okay, so there is a fine balance. So you need sun to produce vitamin D. Okay, but in other words, so this is the disease burden, and then exposure to UV radiation. And so if you have little to no exposure to UV light, that is, you just stay indoors all the time, you could get skeletal disease. Vitamin D insufficiencies will cause other kinds of illnesses. And then on the other side, if you're always outside and not protecting your skin or eyes with like sunglasses or something, then you'll get skin cancers or eye disease, cataracts, for instance. And so there's this kind of minimum exposure risk that you need some exposure but not too much. Okay, and so there are other instances of this. I guess, does anybody know of anything you can think of that kind of too much of it would be bad, but too little? Actually, I guess, too little is bad, too much is bad, and there's kind of like a medium amount that you should ingest or something like that. Anybody think of something?
I guess it goes for everything, moderation, like sugar, for example,
Mm-hmm.
or salt or cholesterol or anything like that.
Yeah. Vitamins, for instance. If you don't take vitamins at all, there's we need really some because we're not getting enough through the foods that we eat. But if you overtake, they can either build up in fat or cause other illnesses. Actually, it's interesting. Water is something that if you take in too much water, it can cause also problems. So yeah. All right. The UV index, I have a couple websites here. The UV index, not unlike the air quality that we looked at. The CMU colors, remember, maroon was bad for air quality. UV index, too, toward our colors, when it's getting into the reds, maroons, that means, really stay indoors, okay? So it's all color-coded. Green means, kind of what we have really today, UV index of 1 probably or something like that. But then in the summertime, we'll probably hit in these regions here, 8 or 9. There's a couple websites that I have bookmarked here. You can look at current ones. So, if we were to look at today here in Mount Pleasant. Yep, so it's a 1. Okay, so yeah, you don't have to do really anything except, it warns you, even though it could be low, reflection off of snow can double the UV strength. They do say, even today to put on SPF 30. I think it's more cautionary and more when it gets to these regions is where it's most important before you go out. But if you want to, compare kind of archived, that's what this other link is. So if you want to know, what, is an activity for your students, for instance, let's look today and then let's look at the UV index sometime in the summertime and compare. That is this website. Okay, so it just shows you kind of, all the way to just last year. And we can say, I don't know, let's look sometime in the summertime here. So like mid-July sometime. I guess I already clicked on this one. Okay, and it's showing, Detroit, for instance, I guess is closest to us in this. I don't know if they have Grand Rapids or anything. No. So yeah, so Detroit was a 7, for instance, okay? Versus if you, click it during January or something, it's probably a 1, okay? So, and then you're looking at some of these others like LA, what was the highest there? I guess it looks like a number of ones are at 11, okay, which are at the highest end, okay. So, as you would expect, the factors that govern UV indices is the ozone concentration in the atmosphere, okay, and we're going to talk about depletion today. That's really the big topic of today. Your elevation and the cloud cover, okay. So elevation is really important as well because, if you're above the clouds, for instance, you're going to get very different ozone or UV impingement on your skin versus, what the forecast may say. Okay. So the regions of the atmosphere, so I guess we already looked at this in a previous chapter, so we're going to be talking about this region today. So the stratosphere, so that's where all the ozone is, its greatest concentrations. In the first chapter, we were concerned here, the troposphere. So that is a bad thing, and then the stratosphere, that's what we want ozone to be in. It's actually interesting. So if you have been in a plane landing in Denver, you'll notice that the plane makes some interesting noises or something. So, there's fewer air molecules. So as you go higher in altitudes, there are fewer air molecules. And so you don't have as much natural natural friction that helps slow the plane down. So they have to really Do some things with the wings, those little flaps that come down in the wings, so you have to spend a greater amount of energy or do some things in the plane to stop the plane. Okay, so because you're landing at a higher altitude in Denver, and likewise, in Denver versus something closer to sea level like New Orleans, it'll take longer to cook food too, and so this has to do with when you boil something. Okay, so I think I lost connection here. There we go. So when you boil something, really the boiling point of something is the temperature where the vapor pressure of the liquid just exceeds or meets the external pressure. Okay, whoops, a little cut off there. There we go. Okay, and so depending on what the external pressure is, that's going to affect, how easily molecules from your liquid escape. Okay, and so since at higher altitudes you have a lower pressure, okay, atmospheric pressure, okay, then that means that you don't need as much of a temperature to have the molecules of water escape, for instance. And so water will boil at a lower temperature. And so, if you're cooking foods at higher elevations, you have to cook them for longer just because, your water temperature is not so high. Okay, and there are a number of little calculators online. So for instance, this one, it's showing the boiling point. If we do it in Celsius here. So the boiling point of water at sea level is, as we know, 100 degrees. But if we go up, let's say 10,000 feet, now it's only 90 degrees. Okay, and so this will affect, the steeping temperatures for teas, for instance. Okay, so for instance, there's certain black teas that really will not steep properly at elevated temperatures just because you need a higher temperature to, diffuse all of the goodness out of the tea bag. Okay, so anyway, all right. So any questions? Is that kind of familiar to you, probably from other classes, etc.? Okay, so the ozone layer is normally only 20 to 100 parts per billion in the troposphere. If it gets any higher than that, that's where you start to, it burns your eyes, etc. So it's not a good thing. In the stratosphere, it's orders of magnitude larger. So you're talking anywhere 12 to even up to 20,000 ppb level in the stratosphere. And so this is kind of the region where it has the highest concentration. What's interesting, and something that we're going to talk about today in more detail, is that the ozone concentration actually becomes greatest near the poles. And so North Pole and South Pole, like over Antarctica. And so the reason for that, I guess, does somebody have a reason for that? So why is the ozone concentration greatest above like Antarctica versus above the equator or something like that?
Is it because it's cold?
Yeah, so cold, definitely. Yeah, so we're going to see here in just a few slides that, I guess we already talked, that the UV light is able to break apart ozone. And so there's a natural cycle that ozone's broken into oxygen, and then oxygen goes back to ozone. And it's this natural cycle. But you need sunlight for ozone to be depleted. And, it's very cold, so you've got these cloud formations that form. And there's also a lack of sunlight in general in the pole regions, just due to the tilt of the Earth. And so yeah, it really has to do with those regions or reasons. Yeah. Okay. Ozone concentrations. It's a really weird unit. So I haven't seen this for any other quantity in the atmosphere. They call it the Dobson unit, and it's really just kind of visualizing if you have a whole column of ozone, if you excuse me, if you smash it down into a certain millimeter thickness, then that corresponds to the Dobson unit. So for instance, if you compress ozone at freezing, so 0 degrees Celsius, to form a 3 millimeter thick slab with a pressure of 1 atmosphere, that's 300 Dobson units. And so if you had 500 DUs, then that's a 5 millimeter thick slab, etc. So it's really related to compressing this down, something we don't do really in practice, but the unit is, I guess, just so you can compare, it's how much you can compress this column down, and then what's that thickness that's left over. Okay, so kind of a weird unit, but just one way to compare concentrations. That's, I guess, how to report units. The way that it is measured, there's actually a few different ways that you can measure ozone in the atmosphere. So balloon sondes are fairly common, where they send it up into the stratosphere, and they have a measuring device, so a detector here that will detect the concentrations. This is actually useful to get information, about up through the stratosphere. So seeing how it will vary, I guess, based on altitude. Ground-based systems, you can shoot laser beams up, and depending on deflection of the laser beams, you can get information about how thick the ozone layer is. And then you can use aircraft or satellites. So again, satellites you can use shoot lasers through the layer, and then if it has a certain bend, you shoot it, and then when it comes back, depending on that angle, you can get information about the thickness of the ozone layer. I think in the textbook we show the space shuttle. It's called limbing, where you can actually look at the ozone layer from beside it. Okay, so when you're actually flying up, you can actually see the ozone layer above the Earth's surface and gauge. You can actually measure how thick it is, and so that would be, I guess, high altitude aircraft. Okay, so there's a variety of ways you can actually measure that. I think a lot of people, I think the number one is still this, sending up balloons into the atmosphere, upper atmosphere. Okay. So we looked at Lewis structures, and so let's talk about the Chapman cycle. So this is something that you could be asked questions about on an exam. Not to put this down exactly like this, but just be familiar with, I guess, the parts of the cycle. So in other words, the most important parts of the cycle are really just 3 parts. And so you've got oxygen that breaks apart into 2 oxygen atoms. And so to be a little more explicit, we could say this. Okay, and so this dot means that it is a radical species, okay, which means very reactive. Okay, and so it's really breaking apart into something that's very reactive, and it's going to react with anything around it. And so if it finds a water molecule, it's going to react with that, okay, but it'll more often than not find oxygen, okay, and so that's why it reacts with that to form ozone. Okay, so that's really the first part of the Chapman cycle, is where you're breaking apart oxygen, and that is by again, the UVC. Okay, so that's why all of the UVC radiation, it doesn't reach Earth or the troposphere, is because of these reactions, really. Okay, so then once you have ozone, then it could also react with those radicals, okay, to get back to oxygen, okay, and then you're kind of back to where you started. Okay, so really the cycle is just constantly forming, so forming ozone and then depleting ozone through, these cycles, okay. And then you've also got, ozone, you've got UVB that can break that apart, okay, to go back to oxygen atoms and oxygen molecules, okay. So this kind of goes, it's kind of a mini cycle, this one here too. But the main one is this, and then that, and then it goes back to here, okay. So these are a natural series of reactions that happen, and you reach a certain equilibrium of ozone, okay? And so, as we said, you're going to have greater concentrations in some parts of the world than you are others, like cold areas. And, it's totally a natural cycle. But what happened is, years ago, they discovered, like in the 80s, that there was a hole. And so there's a website I'm going to take you to in a second here that shows the ozone concentrations over time. And what they noticed is from 79, these are all, by the way, this is where Antarctica is, and so it's all centered around there because that's where the greatest concentration of ozone is during the winter months. And that's where the hole was developed. And so purple here is a bad color again, so it's showing low concentrations. And so this is what the trend was, that from 79 to like a decade later, there was this hole, and it was getting even worse. And so you can see that with actual data here, with all these different stations reporting here. And it's variable, so you'll get depending on the months of the year, go up and down, okay. But if you're looking at kind of the minimum amount, you can see it going down and then it's going up. It's kind of going back up, but I'm going to show you it's really not improving as fast as what they thought it would, okay. So the problem is that ozone can be naturally destroyed by water molecules, and so you've got these radicals that form. But again, that's a natural cycle, so why wasn't it depleting? If it was just due to water, for instance, why was it okay in the 70s versus then the 80s you had a hole in it? So some discovery or some scientific research started to find out, is there something else in the atmosphere that's causing this depletion? And and this really was the smoking gun evidence, okay. And so this shows the concentration of ozone in the atmosphere and stratospheric chlorine concentrations. And so you can see as chlorine concentrations went up, ozone went down, and there was this direct relationship between the amount of chlorine in the atmosphere. And so, then, this was really a shocking discovery. And then we had to think, well, how is chlorine getting in the atmosphere? And so then we looked at chlorofluorocarbons, or CFCs, were at that time really prevalent. And so they were used, anything from deodorants to refrigerants. It was just really pervasive. And they've got really good properties. They're unreactive. They serve as really good propellants, for deodorants, those kinds of things. But good refrigerants. But they will undergo this reaction to kick off a chlorine atom. Okay, and so I want to show you one of these simulations here. So if I go back here, this is a pretty cool simulation. So CFCs in the atmosphere. Okay, so if we look at what happens to a CFC molecule, okay, if I kind of rotate it like that. Okay, so the green atoms are fluorine, yellow is chlorine. And so if microwaves hit the molecule, it doesn't have enough energy to break apart molecules, but it will rotate, okay? And then infrared, if I hit it with an infrared beam, there we go. So you can see, I don't know if you saw that, but now the bonds are stretching more at a greater frequency kind of thing. These should be also stretching. I don't know why they're not, but yeah, so you've just got energy enough to stretch and bend bonds. And then the visible, nothing really happens to it. In the UV though, so this is where you break apart a chlorine atom. And so it's not maybe so obvious right now why, if you have this molecule, okay, why is it that bond that breaks? Okay. And so the reason for that is it has to do with the orbitals that are involved. So when you're forming a bond, between a carbon versus a chlorine versus a carbon versus fluorine, you can look at really like the size of the atoms is maybe the easiest way to think about it. And so if you have that versus like that or something like that, okay, so if these are the sizes of the atoms, okay, so if you have two small atoms that approach one another, they can come together more closely and have a much stronger bond versus if you have something really large that is trying to overlap with something that's small. The only thing that is really overlapping is just kind of on this edge here. Okay, and so in general, as you go down a group, the bonding becomes weaker. Okay, and that's for any types of compounds really. Okay, so CF, so if you're looking, I guess, at strengths, CF will be a stronger bond than CCl, which will be stronger than CI, for instance, if you go like toward the bottom of that group. Okay. Okay. So that's why you are preferentially going to break apart a chlorine, and then another one will break off too. So this will also break off. So really, for one molecule of this, you're getting two chlorine radicals. Okay. So again, they have the dot here, which means really, really reactive. And so it was found that this can also go after ozone. And so you form this, and then that will hit another oxygen atom that's around, and so then you end up with more chlorine in the atmosphere. And so it's kind of this cascading reaction where you get these that then attack ozone, which then attacks more oxygen to give you even more chlorine radicals. And so it was really increasing the concentration of stratospheric chlorine. Okay. So why over Antarctica in particular? So if you look, and we're going to look at this in a second, but if you look at the actual holes, the ozone holes, they are biggest over Antarctica. And you can see why with this. It's kind of a busy figure, but if you look at the temperatures, sort of the average temperatures in around the North Pole, the Arctic, it gets cold. These are temperature like minus degrees, so you're in that range of like minus 70 to minus 80 something in the Arctic. But in Antarctica, it's much colder. You're in like minus 95s, minus 90. Okay, and so there's something called polar stratospheric clouds that are linked in helping these reactions. And I'm going to show you a video of this just in a bit to show kind of how that happens. But you can see that Antarctica is underneath that cloud formation. So in other words, you can get these PSCs forming in the Antarctica really anywhere from like May to October, okay? Whereas in the Arctic, really in July, you're kind of in temperatures less than that, okay? But it's not for most of the year you don't have these cloud forms, okay? And so because of that, it's always going to be worse over Antarctica, okay? And so let's look at the actual data. So this is the website, Ozone Watch, gsfc.nasa.gov, okay? And so this will show you movies of, what's going on, in both hemispheres, really. And so if we look at the northern hemisphere, so in the polar region, if we look at, let's say 19 to 20 here. So this kind of shows you over time what that hole's doing. And again, blue, it means low amount. Blue or purple means low amounts of ozone, stratospheric ozone. You really don't see any real hole developing, right? So there's a little bit, but it's not a dramatic hole in the polar regions, okay? So this could be due to, as I showed, during those months where you are getting some polar stratospheric clouds forming, but it's a very short time of the year. Versus if we look in Antarctica, so let's look at this past year, so 2019. Maybe. Just thinking about it. There we go. Okay. So in July. So August. So now you can see a little bit of purple even forming in there, right? So magenta, kind of purple. Okay, definitely there as well. Okay. So this actually was the best year on record since like 1980 something. Was 2019, and they figured that, remember we had the polar vortex where that last winter did not want to stop kind of thing, so it was really, really cold spring, etc. And so they figured the polar vortex had something to do with how mild, I guess, the ozone hole was, because if you look at the previous year, so if you look at 2018 as a comparison, you'll see a much more dramatic hole that formed. And this is more typical, really, for most years. So right in August, September, look at that. Really dramatic hole right there is the worst, really. So September, October. Okay, and then as it starts to warm up, now those polar stratospheric clouds go away, and then the ozone kind of replenishes. Okay. And so, so here's a little video that shows. I hope I did it. Here we go. Yeah. So it kind of shows the reactions, and so hopefully you can see and hear this. Let's see. Yeah. Can you hear it as well?
Yeah.
Okay. Cool. Cool.
The Antarctic ozone hole is an annual springtime event above Earth's frozen southernmost continent. Conditions above Antarctica magnify the destructive potential of a changing atmosphere. Naturally occurring polar stratospheric clouds, man-made CFCs, and the return of sunlight set off a destructive chain reaction that decimates huge portions of the ozone layer, a critical protection to life on Earth. Stratospheric ozone is necessary because it blocks harmful UV radiation given off by the sun, a primary cause of skin cancer and cell damage in plants and animals. Throughout the 20th century, production of chlorofluorocarbons, or CFCs, were manufactured as a safe, non-toxic replacement for use in refrigeration, air conditioning, and as a propellant in aerosol cans. Growth in CFCs took off worldwide with peak production of over 1 million metric tons per year. But whereas CFCs are safe and inert in the lower atmosphere, they do undergo significant reactions in the stratosphere, where they are exposed to powerful ultraviolet radiation not seen at the surface. Scientists began to notice a springtime depletion of stratospheric ozone, and in 1974 linked it to the chlorine in CFCs. In the early 80s, the depletion increased dramatically, and the need for controlling CFCs became urgent. In 1987, 27 nations signed the Montreal Protocol to reduce substances that deplete the ozone layer. A further worsening of the ozone depletion was avoided, but natural processes remove CFCs at a very slow rate. Continued monitoring of our atmosphere, the ozone layer, and the annual Antarctic ozone hole need to continue. The South Pole is an ideal location to do this. The Amundsen Scott South Pole Station was built at 9,300 feet above sea level, on top of the Antarctic ice sheet. The site has been continuously occupied since 1956 and is an ideal location for many scientific observations. NOAA's Atmospheric Research Observatory, located in the protected clean air sector, measures the cleanest air on Earth. For over 30 years, NOAA scientists have launched balloons from the South Pole to monitor the ozone layer. The balloons rise to over 100,000 feet and collect high-resolution data about the ozone layer. Because of its location at Earth's southern axis, South Pole experiences only one sunrise and one sunset per year. As the Earth orbits around the Sun, the two equinoxes mark sunrise and sunset at the poles. When the sun finally sets after 6 months of day, 6 long, cold months of night begin. Without sunlight, it gets very cold. In the darkness of winter, wind patterns stabilize around Antarctica, preventing warm air from mixing in. This barrier allows the cold air over the continent to get even colder. This is the Antarctic polar vortex, a key component in the process leading to massive ozone destruction. Because of the Antarctic polar vortex, stratospheric air temperatures above Antarctica can plunge well below negative 80 degrees centigrade during the winter. Polar stratospheric clouds form only at these extremely cold temperatures. Let us imagine an ice crystal formed in a polar stratospheric cloud. Reactions in polar stratospheric clouds perform two functions critical to ozone destruction. Stable reservoirs of chlorine in our atmosphere combine on the crystalline surface to release molecular chlorine. The molecules with the ability to restabilize chlorine remain stuck to the ice crystals. In the cold, dark conditions above Antarctica, ice crystals begin to settle out, removing themselves from the destructive chlorine molecules now present in the ozone layer. High above Antarctica, weeks before sunrise will even reach the South Pole, energetic photons from the sun begin to strike the molecular chlorine within the vortex and kick off the process of destroying the ozone layer. Chlorine-free radicals destroy ozone. The resulting molecules bond together, but they are weak and easily broken. Light from the rising sun is strong enough to re-release the chlorine atoms, allowing them to destroy even more ozone. And the catalytic cycle repeats itself. Each chlorine atom can destroy thousands upon thousands of ozone molecules. Chlorine, in a similar reaction with bromine, completely wipe out entire sections of the ozone layer. Throughout August, September, and October, while the vortex remains strong, chlorine completely decimates the ozone layer, and the Antarctic ozone hole fully forms. Eventually, the vortex breaks apart, and molecules with the ability to stabilize free chlorine mix back in, along with ozone from the mid-latitudes. The Antarctic ozone hole fills back in, until next year.
Okay. All right, so the question is, so the Montreal Protocol was signed, and the production. I guess I don't have it in a slide. Or yeah, there it is. Yeah. So the Montreal Protocol was signed, and then so production of CFCs, drastically went down. So this was really a case study of, countries can get together to do something, unlike, where there's now kind of some holdouts with climate change, our country in particular right now. Every country got together, signed it, and, there were very few places that were producing these CFCs. And so then, they started to see, the levels of the ozone hole, that they were kind of, stabilizing at least. And so they figured that, we would get to 1980 levels, back to, the levels, pre when we were putting in all these CFCs, in the year 2070. So it's going to take a long time. We still have all these CFCs that are still in the upper atmosphere that are still, causing, these holes. But what you notice in the Ozone Watch is that it's really not, it's going a lot slower than what people even imagined and so or calculated. And so, if you're looking at annual records here, I don't know if you can see, this is really small. But this is going all the way from 1980. This is the average minimum ozone, or I guess maybe the better one is this is the ozone hole area. And so we can see, even in 2006, it kind of dropped a little bit, but then it came back up. And so as of 2019, it was, as I said, the smallest since back in 1980. But that was kind of a special year because of the influence of the polar vortex. So it'll be interesting to see 2020 how it plays out. It'll probably be back up here. And so a lot of studies have been devoted to why is it really not improving? We don't have any CFCs being produced anymore. So what else could it be? And so there were some papers that there we go, that were published that actually found that we are still producing some chemicals that deplete ozone, and they actually were not included in the Montreal Protocol. And so even though, Montreal Protocol said, no more CFCs, so we took care of that, but there are a couple that are still being produced, still used a lot, that also cause the same effect. And so one of them is carbon tetrachloride. And so if I show you the structure of that, whoops, did I lose? Yeah, screen mirroring. Here we go. So carbon tetrachloride, I guess you've seen that before, right? So it's this one with all these around it. Okay, so that's carbon tetrachloride, and then the other one is methylene chloride. So this one, okay, and so that is just that, okay, with hydrogens in there. Okay, so those two, and it seems surprising, really, that when they were looking at the Montreal Protocol way back, that they didn't think of other chemicals that were being produced and also contain chlorine, and why didn't they outlaw those at that time? And so it turns out that we are still releasing millions of pounds of these in the air, and so these have the same effect. I mean, it's the same chemistry, right? You know, UV light breaking apart carbon chlorine bonds in each of these, right? That and Cl, so it can break apart all these and still form chlorine. And so until we also stop producing these, I don't know, you know, the level of these ozone holes are still going to remain constant. Okay, so so it's kind of showing you that CFCs are not the only thing to blame. Okay. All right, so this is where, you know, people were looking at alternatives then to CFCs, and people developed these ones. And so again, you know, if you're going to compare this, I guess, yeah, this one. So this was the first CFC that they found, and that was, you know, to stop production of it. And you can see, you know, for every molecule of this, you have two Cl radicals. Okay, so, you know, the easy choice would be, yeah, let's just come up with this one. So you only have one of them that can be produced. So that helped a little bit. And it, I guess, you know, it has very similar properties to this one. So, you know, in the short term, people could use it for really the same applications. And then people went to this one, which worked pretty well. And then they went to these. So there's all kinds of different varieties now that people can, you know, use. And I think, you know, commercial ones now are either this one or that one, or some common types of refrigerants, for instance, in vehicles are these varieties. Okay, so different freons. But the problem with these then is that even though now they do not produce chlorine that can, you know, deplete ozone, stratospheric ozone, they actually are greenhouse gases, and so they play a role in climate change. Okay, so you kind of substitute one problem for the other. Okay, but at least, I guess, you know, we're trying to address, you know, one of those problems. Okay. All right. So sunscreens. So, you know, with UV coming through because of less ozone in the stratosphere, we have to block out more of it these days. And so sunscreens work really a couple ways. So it's just used to block, you know, UV light. And so I'll show you this little simulation here. And so this is, you know, the easiest way to think of sunscreens is really this. So you have different sized nanoparticles, and so if we have very large nanoparticles and then we fire photons of UV through, you know, you can see that most of them got through. Okay, like 13% were stopped. And as we work our way down, you know, more of it will be stopped. Okay, but as you get smaller and smaller, the surface area of your nanoparticles are greater. And so here, you know, you've stopped all the UV light kind of thing with 10 nanometers. Okay, this is kind of, it's showing a couple things. The size is changing and the number of them are also changing. But in general, as you as you decrease the size of nanoparticles, then you increase their surface area. And so that means that they will block more UV light. Okay, so you've got, this property of sunscreens is really just a simple blocking. You've got sunscreen that contains nanoparticles of something. Okay, but then you could have some sunscreens that contain only organic molecules. So for instance, these ones. Okay, so you could just have a series of really kind of complicated organic molecules, and these are not nanoparticles actually. And so the reason these are used is just due to absorption via certain energy levels. And so for these organic molecules, I don't know if you can see, but they have these double bonds in here. So in these rings, do you see that you've got like single bonds, double bonds, and that? So wherever you have these double bonds, you can absorb radiation and then promote electrons from one energy level to the other. Okay, and so without getting into the details, you really have a certain ground state, and then when UV light hits a molecule, then you absorb that energy to go to an excited state. Okay, and in that process, you are absorbing the UV light. Okay, so you can design sunscreens that, they have these nanoparticles kind of for blocking effect. And the ones that are most often used is titanium oxide or zinc oxide. And these are most effective because they have these energy levels as well. So zinc oxide, for instance, will absorb as UV light comes in, it'll absorb it and then cause an electron to be promoted to a bottom energy state to a higher energy state. Okay, and so there's just those couple reasons. Okay, so it's a blocking effect, and then it's also an electronic transition effect. Okay. All right, so the last little thing I want to show you is about the SPFs. So this is something that's not really so understood so clearly, so I just wanted to show you this.
Sun safe, but sunscreen labels are confusing. SPF, UVA, UVB, OMG. We'll explain the science so you don't get burned. Hey Chemketeers, Carmen here. Summertime means fun in the sun, but this season, the U.S. Senate is turning up the heat on the Food and Drug Administration. Senators want the FDA to lay down the law on sunscreen labeling. Anything over SPF 50, lawmakers say, should just be labeled as SPF 50+. Why? Sunscreen protection pretty much tops out there. Numbers higher than SPF 50 are just misleading, and probably a waste of money.
Wait, so my SPF 70 spray here isn't extra awesome? I was always taught that more is more.
Well, Sophia, it's complicated. Allow me to shed some light on sunscreen chemistry. SPF stands for sun protection factor. Think of a layer of sunscreen like a really thin bulletproof vest, and the sun's rays as a barrage of bullets. Sunscreens absorb or reflect UV radiation from the sun before it can penetrate your skin and give you a sunburn, or even worse, skin cancer. Chemists have a measurement called absorbance. In the lab, you can shine a light on something and then figure out how much of that light comes through the other side. You can test sunscreens the same way. You'd think that SPF 30 would have 2 times as much absorbance as SPF 15, but it doesn't. And look, SPF 50 isn't that much better than SPF 30. We're maxing out here, people. Here's another way of looking at it. After SPF 50, you're barely getting any more bang for your buck. Sky-high numbers might make you think you're safer, but the evidence says otherwise. You should also know that no sunscreen blocks 100% of UV rays. And one last thing. SPF only measures how effective sunscreen is at blocking UVB rays. UVB rays are the primary cause of sunburn, but UVA rays penetrate even deeper into your skin. They're linked to premature aging and skin cancer, and play a role in sunburn too. Experts have yet to agree on a system for measuring UVA ray protection. For now, there's a pass-fail test. If a sunscreen passes, it gets labeled broad spectrum. So remember, apply plenty, reapply often, and don't waste your money on anything over SPF 50. That's Speaking of Chemistry. You can get more information at cen.acs.org. Speak your mind down below, and don't forget to subscribe and share.
Okay. All right, so I think that is it as far as sunscreens and I guess, the difference between sunblock and sunscreens, I guess, is one last item here. So sunblocks sunscreens. So these are, what you've seen, probably lifeguards where they have, like a white nose or something like that. So it's generally not transparent. These are typically like greater than 100 nanometer sized particles, so pretty large particles, and it is just using blocking, I guess as its name implies, right? It's just blocking UV. Whereas sunscreens, these are generally transparent, so they will have, less than 30 nanometer particles in them, and it's really an absorption process. So these are ones where, as we talked about earlier, right, where you're moving electrons from lower energy levels to higher energy levels. Okay, so that is it for this chapter. I was wondering whether I should go on to the next one. I think I want to leave it with that today. And then on Wednesday, what we're going to do is start climate change, and we're going to start by looking at how to name other types of compounds. And so that'll be really the Wednesday's lecture will be a lot of like naming inorganic compounds, and then moving on from there, seeing where carbon goes in the globe. All right. So, any questions about anything today? I feel that when we're not face to face and just PowerPoints, I go faster. But I guess any questions? No? Okay. All right. Well, I guess that is it for today. And I will see you all on Wednesday. And in the meantime, stay safe, stay healthy. And let me know if you have any questions. I guess you got my email about the online stuff. So work on your readings for these next few chapters. And we will go from there. All right, so take care. Enjoy the rest of your day.